cogeneration involves using a fuel, such as natural gas, to drive a turbine that generates electricity. The waste heat from this process is then recovered and used for heating, cooling, or other thermal applications. To determine if cogeneration is suitable for a facility, evaluate its viability based on factors such as gas availability, thermal and electrical load profiles, and potential savings. Proper system sizing is critical for optimal efficiency. A cogeneration system should be sized to meet the base electrical and thermal loads of the facility. Securing a reliable gas supply is essential. Consider backup arrangements to minimize operational risks. Maximize energy efficiency by utilizing waste heat recovery systems such as heat exchangers and thermal storage. Implement a comprehensive monitoring system to track performance and identify areas for improvement. Factor in operating costs, including fuel, maintenance, and labor, when evaluating the economic viability of cogeneration. Compliance with environmental regulations, including emissions standards and monitoring requirements, is also critical. For further information, consider the Department of Energy's Combined Heat and Power Technologies website. The CHP Alliance publishes the International Journal of CHP and Distributed Energy. There is also the Cogeneration and Distributed Generation Handbook by William L. Kramer, Cogeneration, a comprehensive introduction by John W. Mitchell, and Combined Heat and Power, a clean energy solution by the World Bank. Conduct a thorough due diligence. Engage experts to assess the project's technical, economic, and environmental feasibility. Research government incentives, tax credits, and financing programs available for cogeneration projects. Consider partnering with a qualified developer who can provide expertise and support throughout the project lifecycle. Staying informed about industry trends and advancements is also important. Attend industry conferences and seminars to stay up to date on the latest cogeneration technologies and best practices. The evaluation of the electrical load profile is a very critical aspect. This evaluation requires an understanding of the facility's electricity consumption patterns, including the peak demand, average demand, and load factor. The peak demand is the maximum amount of power required by the facility at any given time. The average demand is the average power consumption over a specific period, typically a month or a year. The load factor is the ratio of average demand to peak demand, indicating the consistency of electricity usage. A high load factor suggests a relatively constant demand, which is favorable for cogeneration. To develop an electrical load profile, data can be collected from utility bills or from a dedicated energy monitoring system. This data is then analyzed to determine the facility's electricity consumption patterns. The electrical load profile helps in determining the appropriate size of the cogeneration system. The system should be sized to meet the base electrical load, which is the minimum continuous electricity demand of the facility. Sizing the system to match the base load ensures that the generated electricity is fully utilized, maximizing the economic benefits of cogeneration. The thermal load profile is just as important, and it involves analyzing the facility's thermal energy requirements, including heating, cooling, and process heat. The thermal load profile should consider the magnitude and duration of these thermal demands. Data for the thermal load profile can be gathered from building automation systems, process control systems, or by conducting energy audits. A detailed thermal load profile helps in determining the type and size of heat recovery equipment needed for the cogeneration system. The waste heat from the electricity generation process can be used to meet these thermal demands, improving the overall efficiency of the system. A feasibility study is another step which involves a comprehensive analysis of the technical, economic, and environmental aspects of a cogeneration project. The technical assessment should evaluate the suitability of different cogeneration technologies, such as reciprocating engines, gas turbines, or fuel cells, for the specific application. The assessment should also consider factors such as fuel availability, space requirements, and grid interconnection capabilities. The economic assessment should evaluate the financial viability of the project, considering factors such as capital costs, operating costs, fuel costs, electricity prices, and potential revenue streams. The environmental assessment should evaluate the environmental impacts of the project, including air emissions, water discharge, and noise pollution. A feasibility study should also identify potential environmental permits and regulatory requirements. Selecting the appropriate cogeneration technology depends on several factors, including the size of the facility, the electrical and thermal load profiles, the fuel availability, and the environmental requirements. Reciprocating engines are suitable for smaller facilities with relatively constant electrical and thermal loads. Gas turbines are better suited for larger facilities with high electrical and thermal demands. Fuel cells are an emerging technology that offers high efficiency and low emissions but may have high capital costs. Waste heat recovery is a critical component of a cogeneration system, and it involves capturing and reusing the waste heat generated during the electricity generation process. The waste heat can be used for various applications, including space heating, domestic hot water, process heating, and absorption cooling. Heat exchangers are commonly used to transfer heat from the exhaust gases of the engine or turbine to a water or steam loop. The hot water or steam can then be used for heating or cooling purposes. Thermal storage systems can be used to store excess heat for later use, improving the overall efficiency of the system. The economic benefits of cogeneration depend on several factors, including the price of electricity, the price of fuel, the efficiency of the cogeneration system, and the operating hours. Cogeneration can reduce electricity costs by generating electricity on site, reducing the reliance on the grid. Cogeneration can also reduce fuel costs by utilizing waste heat, improving the overall energy efficiency of the facility. Government incentives, such as tax credits and rebates, can further improve the economic viability of cogeneration projects. The environmental benefits of cogeneration are another key factor, and they include reduced greenhouse gas emissions and improved air quality. Cogeneration can reduce greenhouse gas emissions by improving energy efficiency and reducing the reliance on fossil fuel power plants. Cogeneration can also reduce air pollution by utilizing cleaner fuels and reducing the amount of pollutants emitted into the atmosphere. Cogeneration projects may be subject to various environmental regulations, including air emission permits, water discharge permits, and noise pollution regulations. It's critical to comply with all applicable environmental regulations to ensure the sustainability of the project. Maintaining the cogeneration system is important for ensuring its long-term performance and reliability. Regular maintenance should include inspections, cleaning, lubrication, and replacement of worn parts. A preventive maintenance program can help identify and address potential problems before they lead to equipment failures. It's also important to monitor the performance of the cogeneration system and track key parameters such as electricity generation, heat recovery, fuel consumption, and emissions. The monitoring data can be used to identify areas for improvement and optimize the system's performance. Interconnecting the cogeneration system to the grid may be required to sell excess electricity back to the utility. The grid interconnection process involves meeting the utility's technical requirements and obtaining the necessary permits and approvals. The interconnection agreement should specify the terms and conditions of the grid interconnection, including the pricing of excess electricity. Cogeneration can provide a reliable and resilient power supply, particularly during grid outages or emergencies. Cogeneration systems can be designed to operate in island mode, providing electricity to the facility even when the grid is down. Cogeneration can also improve the overall energy security of the facility by reducing the reliance on external energy sources. Cogeneration projects often face various challenges, including high capital costs, complex regulatory requirements, and the need for specialized expertise. Careful planning, thorough due diligence, and collaboration with experienced developers can help overcome these challenges. It's also important to stay informed about the latest cogeneration technologies and best practices to ensure the success of the project. Cogeneration systems can be designed to integrate with other renewable energy sources, such as solar and wind power. For example, solar thermal collectors can be used to supplement the heat recovered from the cogeneration system. Wind turbines can be used to generate additional electricity, reducing the reliance on fossil fuels. The integration of cogeneration with renewable energy sources can further improve the sustainability and environmental benefits of the project. Consider district energy systems where cogeneration plants can supply heat and power to multiple buildings or facilities in a defined area. District energy systems can improve energy efficiency and reduce greenhouse gas emissions by centralizing energy production and distribution. District energy systems can also provide a more reliable and resilient energy supply to the community. When evaluating a cogeneration project, it's important to consider the total cost of ownership, which includes the capital costs, operating costs, maintenance costs, and fuel costs over the lifetime of the project. A life cycle cost analysis can help compare the total cost of ownership of different cogeneration technologies and identify the most cost-effective option. The analysis should also consider the potential revenue streams from electricity sales, heat sales, and government incentives. In summary, a cogeneration project requires careful planning, thorough due diligence, and a comprehensive understanding of the technical, economic, and environmental aspects. By considering these factors, you can maximize the benefits of cogeneration and create a sustainable and cost-effective energy solution for your facility. Remember to involve qualified experts, conduct a detailed feasibility study, and stay informed about the latest industry trends and advancements.